So you wanna escape the world and never return. Then you need an escape velocity. Okay, we're looking at an escape velocity here today, which is the velocity you need in order to escape away from an object and never ever return. The Once you have this escape velocity, you have enough speed so that as you move further and further away from that, planetary body or that solar body, or just another star or black hole, whatever it is, by the time you get an infinite distance away, you will have finally stopped moving. Now, technically, like, you could never get an infinite distance away. It's more of a mathematical construct in that idea. But if we kind of think about it like this, like, we'll go over here. Here is the black hole. Why is that green? That's a black hole. And you were somehow slungshot around it, like, zoom, and you went away. As you go further and further away from the black hole, you are slowing down because it's trying to pull you back. Remember, it's trying to pull you back here due to gravity. So you're slowing down, but as you get further away, that pull is weakening because if we remember, that force it's pulling you back with is gmm over r squared, and as that r squared in the denominator is getting bigger and bigger, this force it's pulling you back is smaller and smaller, which means that you're accelerating in a negative direction or you're slowing down by less and less, which means that just at some point way out here, you have finally, as you keep slowing, as you finally slow down by a little bit at an infinite distance away, your velocity will be 0. And that means you've escaped. That's how we define the escape velocity. Now, interestingly enough, if your velocity out here is 0, this means that your kinetic energy is 0. And the other thing it means is that if you are an infinite distance away, we define the gravitational potential energy as being 0 all the way out at infinity as well. So if you have reached the escape velocity of something, then when you are out at infinity, you are no longer moving and you have no more potential, and that is it. It is done. You are game over. Okay? So that's what we're going to be talking about here. Now, the way we can do this is if we look at the conservation of energy, that's going to be our ticket out of here. And what we're going to do here is we know that at the end of this, our final kinetic and final potential are going to be a 0 and a 0. That's great. We've got 0 kinetic because we're not moving out at infinity, and when we're at infinity, our potential is 0. So all we have to say here is our initial kinetic energy is 1/2 mv squared, and this is actually going to be our escape velocity. That's the velocity we need to escape, and then plus a potential. Now, while we are adding it, the potential energy is thought of as a negative quantity. So when we add a negative number, we're subtracting it, and the potential energy due to gravity is gmm over r. And this is going to equal to 0 plus 0, which is 0. So all we have to do now is solve for this escape velocity here, and we're done. A quick thing that we'll notice is we'll just move the gmm over r to the other side. So we can write this as 1/2 mv squared equals gmm over r, and we quickly notice here that the mass of the object doesn't actually matter. It doesn't matter if you're moving a car, a person, a planet away from an object. The mass of that thing does not matter. And then we just need to get rid of this 1/2, so we'll multiply each side by 2, and then we got to get rid of the square, so we'll take the square root of it. When we do that, we find that the escape velocity here is just equal to the square root of 2gm over r. That is the escape velocity. It's very similar to the orbital velocity, but the orbital velocity, remember, we use centripetal forces to do that, and there wasn't this 2 out in front. We get that 2 due to the conservation of energy in this. So yeah, if for some reason your velocity is less than the escape velocity, then your path could be an ellipse. The object has remained in orbit. And remember, for an ellipse, we talked about ellipses in the ellipse video, but ellipses have eccentricities that are less than 1. If your eccentricity exactly equals 0, you are a perfect circle. Congratulations. So we see up here, we could be a circle or we could be an ellipse. And this is a heavily, flattened out ellipse. We normally don't have ellipses that are that kind of pulled apart, unless you're kind of like a comet or something. If your velocity is equal to the escape velocity, then you're a parabola. The parabola is seen kind of right here like this. We kind of come in, we slingshot around, and then we come back. You're never coming back from that. You just got ejected out. We do this for a lot of space probes. We call it slingshotting them around planets or stars. We can build up a lot of speed and then kind of send them out and change their direction and speed them up. And remember, this is whenever your eccentricity will exactly equal 1. And if our eccentricity is greater than 1 and our velocity is greater than the escape velocity, the path is a hyperbola. And when we have a hyperbola, it's very similar to an ellipse, but it's just kind of a more widened. And your object is once again never returning. Okay, so in either the parabola or the hyperbola case, you're never getting that object back. You have escaped from the system. You're only stuck in an orbit if your velocity is less than the escape velocity. So that's it for escape velocity there. Quick little derivation of it, what's going on with it, how we think about it, and how we see different orbital paths depending on the shape of that ellipse and the escape velocity values as well. So with that, this is finished. Take it easy. Hopefully you don't need to escape anything like this, but if you do, I recommend the slingshot method. So adios.